Okay, so good morning, everyone. This is Shixin Ji, and I'm a third-year PhD student from Brown University, and I'm supervised by Professor Pedro. Today, I'm going to present our work DERCA, which is an accelerator specialized design for the real-time safety critical systems. So speaking of the real-time safety critical systems, what is the most popular one of them? Let's first take a look at an autonomous driving system. Here we have an autonomous driving car, and we will have the camera and the LiDAR as the sensors to check the surroundings. We use the camera to detect the traffic lights and use the LiDAR to detect the obstacles as well as the pedestrians. So with all this information collected, we can then do planning and control based on this information. For example, we can, if we have a red light in front of us, we would probably stop to avoid getting a ticket. So with the prosperity of the deep neural network, which are DNNs, we can do the perception and planning use the DNNs. For example, for the image classification for camera, we will have the MLP mixer, which stands for multi-layer perception and computes using matrix multiplication. And we also have YOLO, which is mainly in CNN, that is compute in convolution. For the LiDAR detection, we also have the point net and point transformer for the point cloud processing. And we will also have reinforcement learning-based planning models. The most important feature of these systems is the safety. So we must design our system so that we do not hit someone. Let's consider this example where a car is running on the way and suddenly a pedestrian going onto the road. And to avoid hitting the person, we should behave as follows. First, in the last frame, the LiDAR does not detect the pedestrian so that there will be no pedestrian and we keep our speed. And in the second frame, we should detect our pedestrian, then we stop our car. And finally, after the pedestrian goes off from the road, we can then speed up. So if we want to ensure safety, the car must react before it's going for 1 meter, so that we have enough space for the mechanic parts to brake. So if the car is running on a highway, for example, 120 kilometers per hour, the gap before we do the reaction is only 30 milliseconds. This means that given the fact that the person can appear between two frames, we have to detect periodically with only 15 milliseconds, and each detection should finish before deadline. What if we do not finish them on time? That is, if we do, for the first frame is the same, but for the second frame, we do not detect the pedestrian on time, so the car will not stop on time. Instead, the car keeps the speed. And as a result, I would not want to describe the result, which is basically a hazard. So this 1 meter or 30 millisecond gap between the person going on the road to the car react is very important. Only with this latency being bounded, we can have a safe and predictable system. So to achieve this bound, there will be many parts in the car working together. We will have the sensors, the engine, and the control system, but most importantly, we will have the computing platforms. We can compute the DNNs using CPUs, GPUs, or we can have other customized accelerator with unique structures like the Grok LPU or Google TPU. On the other hand, the car will have some limitations, which is different from the server or a data center. That is, we have to use battery to power these platforms, and also they have a limited space. So different tasks must share in the same accelerator. And for the accelerator, we need dynamic scheduling and preemption to handle the multitasking so that every task can be finished on time. So what are the features needed for computing the DNNs on such a real-time safety critical system? To answer this question, we need to take a look at how DNNs are executed on CPUs and GPUs. So here is a timeline of running of of MLP model, which is matrix multiplication based. We run it on GPU using PyTorch and recording the trace using the NVIDIA Nsight, which is a vendor-provided profiling tool that allows you to check the details of the execution. So we can see that the execution are actually in blocks. What are these blocks? The large blocks with the void text is actually the linear layer, that is the matrix multiplication. We also have the small layers, which are the non-linear layers, such as ReLU, softmax, and layer norm. Finally, we know that the DNN models are composed of DNN layers, and the GPU schedules them in a layer-wise manner. That is, we launch the CUDA kernels one by one. Each kernel is a layer. And more importantly, without changing the underlying implementation, we cannot preempt within a layer. This could block the tasks with a higher priority. And one layer could actually have a long time to execute, especially when its shape is large. For example, here, one layer can have almost 30 milliseconds of latency. That is almost the gap we have just talked about. So it is true that with the change of the scheduler in CPU, we can do preemption between two layers. However, this is not free. We need to pay the latency for the host-to-device communication, and also there will be other overhead to load the code or data on the GPU, and all other communication or say control overheads. So without customized hardware design, we cannot optimize for these overheads, and they could be an issue. And it is also true that we can split the tensors and change their low-level hardware or software to achieve fine-grained preemption even within a layer. However, first, this is not a native support for, especially for the GPUs, so it lacks flexibility. And for most of the commercial products, like the NVIDIA GPUs, such low-level features are not opened. And even if we can do this, this will require a large amount of human effort. So speaking of what we need, well, we can summary about them. First, as a programmer, we want fine-grained control to preempt within a DNN layer. And for the software part, we want to do scalability analysis to ensure safety. And finally, the overhead is not trivial, so we want to optimize for it. This is exactly what DERCA does. First, we do enable the intra-layer flexible data flow, which offers more than 4,000 preemption points within a matrix multiplication layer of 8K size. And we also provide a cycle-level accurate performance model and analyze it in the limited predictive scenario. And finally, to the overhead, we first implement on our scheduler on chip. And for each preemption point, we can implement flexible selection of how to implement them so that we can reduce the overhead. Finally, on the software side, we integrate with PP placement optimization to remove the redundant PPs. So in DERCA, we choose FPGA as a prototype. We're leveraging its low-level and open flexible control to implement the hardware and the hardware part we need on the FPGA fabric. So this is the overview of a DERCA workload. The input includes the task configs, such as the data flow graph, the period, and the deadline, and also the platform resources and constraints. We first send them to the software stack. And in the very beginning, each task is basically mapped to a sequence of layers. Then we segment the tasks with all the preemption points enabled by DERCA. And we can conduct optimization for each preemption point, which we will talk about more later. And finally, we remove some redundant preemption points by doing the PP placement optimization and do scalability analysis. If it passes, we can export the configurations to the hardware part. That is, we design the hardware accelerator based on the software configurations. So there will be on-chip earliest deadline first scheduler, and there will be an on-chip kernel management module which stores the task set execution procedure from the software part. And finally, we have a P-array plus flexible controller, which is responsible for the computation and preemption. So for the scheduler, the key part of its structure is the heap structure implemented in hardware, and is connected to others with first-in, first-out hardware queues implemented using shifting registers. So this scheduler can handle the release of new job where we insert the new job to the heap and do a heap sort. We can also do, the scheduler can also issue a segment to the accelerator for execution. So, and also when a segment is finished and we can process the feedback from the accelerator. So we can issue the next segment to the accelerator, or if this is the last segment of the task, we can do another heap sort to find the new task or the new job with the smallest deadline. The key feature of our scheduler is that it is deterministic. First, we implement it on the FPGA fabric, so there will be no cache access and no operating systems. Also, with our hardware heap implementation, the one heap sort operation is deterministic, so that one branch that contains one type of event is deterministic. As a result, the whole scheduler can be deterministic. This is also true for other hardware parts of our system. As a result, the DERCA can provide a cycle-level accurate performance model, which we used to estimate the performance even before we deploy them onto the hardware. So the scheduler schedules tasks in a segmented manner, and to execute them, we also need to customize the hardware accelerator part. So how should we partition the DNN layer actually comes from the low-level execution procedures of the accelerator. That is, we use the same accelerator plus different configurations. So here are two matrix multiplications with different shapes. What we do with them is that we partition them to different number of tiles. But for each tile, we use the same execution procedure. That is, for each tile, we load them into the input buffer, we compute them and generate the partial result, and put them into the output buffer. At this time, we do not store them back to the DDR, but we compute the third and the second tile until we finish all of the k dimension, so that we get a complete result of the output. Then we store it back to the DDR. In this way, we can finish the whole matrix multiplication step by step. So what we propose to do is that the potential preemption point is the gap between the tiles. So the question is, how can we do this? Or more specifically, how do we deal with the on-chip intermediate data? What we do is that, let's consider about this scenario, where we are running in the halfway and here a preemption happens. So at this time, the input buffer and output buffer will contain intermediate data, and there will be also other data in the DDR. For the P array, it is empty in the gap, and the DDR is unchanged since that we allocate separate DDR address for different tasks. But what we do is that we need to clean the input and output on-chip buffer. So depends on how we clean them, is that first we can drop it and recompute them later, which is the recompute data flow. Or we can store it and load it back later, which we call it persist data flow. With the recompute data flow, when preemption happens, we drop them immediately so that we can launch the high priority task almost immediately. But when resume happens, we need to go back to the very beginning of this output piece and pay the latency of recompute. For the persist data flow, when preemption happens, we need to pay the communication latency that stores the partial results. And when resume happens, we need to pay another overhead also to load the partial results back before we can continue execution. So the key observation here is that we do not have a dominant beta strategy. For example, if we choose to preempt after the tile 2, if we use recompute, we'll only need to recompute a small number of tiles, but we still need to store and load the whole output buffer using the persist strategy before we can continue. In this way, the store plus load is larger than recompute, so that the recompute strategy is better. But if we preempt after tile 7, with the recompute strategy, we will have a lot of things to recompute. But for the persist strategy, the output buffer size is the same, so the overhead is the same. So that in this way, the store plus load is smaller than recompute. The persist strategy will be better. What DERCA offers is that DERCA can choose the better strategy offline and perform them accordingly at runtime. So how DERCA optimizes for the overhead is that we begin with the hardware operations like load, compute, and store, and to compose the execution length, and also the preemption overhead and resume overhead, which happens we preempt and preempt others and being preempted by others. So as one task can preempt many other tasks, we estimate the preemption overhead using the maximum of recompute and persist. And for each resume overhead, we choose the implementation of the preemption point with a smaller resume operation latency, so that we can optimize for the preemption overhead. Finally, we send them to preemption point placement and scalability analysis, so that we can ensure safe and tight estimation and with the overhead estimated. Finally, let's talk about the evaluation of the DERCA. We randomly generate the periods of each task in one task set and schedule them and collect the success rate of each total utilization, which is the execution time over the period. The baselines are not performing good, especially when utilization is high. And with the intralayer flexible data flow, we can perform better than the baselines. So with only recompute and only persist, they will perform worse as they have higher overhead and they do not optimize for it. So the decreases the success rate. And finally, with the PP placement optimization, we can further reduce overhead and enhance our success rate. We also evaluate DERCA on other workloads, and this shows the similar trend, that is the flexible data flow is much better than the baseline. So finally, we implement the DERCA on the AMD VCK190 platform and choose Charm, which is a state-of-art accelerator, as the baseline. We can say DERCA is actually lightweight. We use less than 5% of additional resource to enable our intra-layer flexible data flow together with the dynamic scheduling. That is all for our DERCA work. Thank you very much.